Okay, so thank you all for coming. So my name is Danny, and I work for Softyne in the UK, where we're building both hardware and software for which allows people to purchase flexible storage in order to build Ceph clusters. So tailored for Ceph, it's sort of like an appliance. I've mainly worked for open source companies in the past, and I spend a lot of time organizing meetups and conferences in the UK. So I'm also one of the co-organizers of this event in the UK, basically. So error detection. So I mainly got interested in this topic after I saw an old colleague give a lightning talk on this subject years ago. So a really talented guy called Jim MacArthur, who has an unhealthy obsession with electronics and robots. I think Matt will know who I'm talking about. But yeah, so he made me curious about error detection and correction and how it relates to RAID and other technologies. So I did some digging around and found that there's actually lots of different ways of doing this, and it's been around for like 70 years. And so I thought I'd give you an overview of a few of the different technologies and how they work. So each one of these techniques have their own pros and cons and trade-offs that you have to consider. So yeah, the idea behind it is to have a set of techniques, codes, algorithms that we can use when we transmit data, so that we know that on the receiving end that the data is inconsistent, and we can act upon that information either by dropping the data or correcting it somehow. But just knowing that it's wrong is obviously a good thing. So yeah, these concepts have been around since before modern computers were born, and even some of the older ideas are prevalent today, so they're still part of a lot of things that we use in our day-to-day lives. So why do we have errors in the first place? This could be a whole bunch of different reasons. It could be human error, it could be network glitches, it could be something really random, like cosmic rays at a chip level or noise on a data bus. These things happen, and they're like way more common than I expected, so way more common than you might think. So yeah, it's an issue. So start off with the most basic form of error detection, which is the parity bit. I don't know how many of you guys have heard of a parity bit. Quite a few, cool. So the idea is that essentially you add a bit at the end of a set of bits, which we call a symbol. So it could be a byte, could be larger, could be less. And that bit counts the number of odd or even bit ones in the remaining symbol. So you can have an even parity bit, which will tell you how many, if there's an even number of ones, or you can have an odd parity bit, which tells you if there's an odd number. So I've done an even here. You can see that for A, for example, there's 2 ones, so that's even, so we have a 1 on the end. For D, we have 3 ones, so that's odd, so it's a 0. And so when you send it, if on the receiving end you have an unmatching number, then you know that there's an error. So this is like really basic form of parity, and it's also a basic type of checksum. And one of the things that you need to think about with this is the fact that if you have more than one error within, or more than one error within the symbol that you're doing, then you're not going to pick up the error, because it's obviously. But the idea behind this is it's really cheap and inexpensive. So in situations where the risk is quite low, you want to use it. So it's quite popular in hardware applications. A lot of microcontroller caches use it. It's used in PCI. It's used in SCSI. It was used in RS-232 serial, and this goes really as far back as the 50s. So they used this. They even had a parity track on mechanical tape drives. So this doesn't let us correct an error, but it lets us know that an error exists. So there's a decimal equivalent to the parity bit. And this is my credit card. You can take a photo and steal my identity if you like. It's an old bank card. It doesn't exist anymore. But basically, this is a decimal equivalent which we use even today. And so something you may not know is that on every credit card, if you pull out your credit card, this will work. The last digit is actually a check digit. And it tells us if the credit card number is valid. So how does this work? it uses something called the Luhn algorithm. So Luhn is a German-American engineer that worked for IBM in the 40s and 50s. And he was also the guy that came up with the idea for information buckets, which we know today as it's speeding up indexing for data retrieval. So it's kind of like placement groups in Ceph is a descendant from this idea. And so the idea is that starting from the right, you double every other digit. And then if it's a double digit, you add them together. And you then sum up the remainder, and the last digit on the end should make it a multiple of 10. And if it isn't, then you know that the credit card is invalid. And so if you've ever wondered, if you've ever been filling a web form where your Wi-Fi is off, but somehow the web form still knows that your credit card is invalid, this is how it works, because it's actually just doing it locally. So one of the main pioneers behind error correction and detection is a guy called Richard Hamming. And so Hamming was a mathematician and professor who worked at Los Alamos on the Manhattan Project in 1945, right in the middle of all of it. And he was on a team which was responsible for programming the IBM machines that they had with the scientists' formulas to check that they were correct. After leaving Los Alamos, he went on to join Bell Labs in 1946, where he became known to be one of the Young Turks. So this was a group of people within Bell that were basically given free rein. They weren't micromanaged or measured by, how many grants have you done, how much teaching have you done, they were just like, get on with it. And as a result, 3 of them ended up getting Nobel Prizes, another 3 of them ended up leading Bell Labs. This guy came up with the term bit, which was previously known as the binary information digit. But these guys are kind of like they built the foundation of telecommunications as we know it today. And so yeah, Richard Hamming, while he was part of this group at Bell, he was working on some physics problems, and he set his machines on a Friday night to do a long, complicated problem over the weekend. Went home, came back on Monday, and he was like, oh, the whole thing stopped very early Saturday morning because of an error. And so this kept happening, and it's very frustrating. And it was quite common to have errors there at the time because they used punch cards, and so punch cards could easily be bent, or when you punch the card, it might not punch properly. So he decided to go on the biggest yak shave ever and move from physics to error correction and try and figure out how to solve this problem. He just spent the rest of his career doing that instead. So he published a key paper a couple of years later called Error Detecting and Correcting Codes in 1950. And he described a few concepts which are just foundation of error correction as we know it. And these are, number 1, the Hamming distance. So this is the distance, this is the number of single bit operations you have to do to a string or symbol that will change it or correct it. So for example, OpenStack days, we want to change it to OpenInfra days. The Hamming distance for that is 5. There's also a concept called the Hamming cube, which is you can basically describe this as a cube, and this can get really big and complicated, but it has various properties that are useful. And the next thing he went on to find was a system called the Hamming codes. And these are way more useful than the basic parity bit for a number of reasons. First of all, it's the first code that allows us to correct errors, and it can also detect errors up to 2 bits. So how does this work? So imagine we have 4 data bits, 1, 0, 1, 0. We put them in 3 circles, which are overlapping, and we put the data bits in the overlapping pieces. So D1, D2, D3, D4, 1, 0, 1, 0. Next, we calculate the parity within each circle for each circle, we calculate the parity bit. So for circle 1, we have 1, 1, so that's going to be a 0. For circle 2, we have 2 1s, so that's a 1. And circle 3, we have 1 1, so that's a 0 again. So this is what we're going to send on the transmission end. And there's our parity bit. So this makes up what we end up sending. As you can see, it's quite expensive in the sense that you need 3 bits for every 4 bits that you're sending. So, right, we've sent it, we've received it, and something's changed. The D3 is now 0. So how do we correct this error? So the D3 changes to 0. We can then recalculate the parity across each circle. So for parity 3, we know that obviously this should no longer be a 0, so there's something wrong there. Same again here. This doesn't quite add up, and the top circle does. So this tells us that it's D3 that's the offending bit, so we could change it back and correct it. So that's the basic idea of how the Hamming codes work. So another use of parity is RAID. So I'm sure all of you have heard of RAID. You've probably all built RAID clusters. So RAID 2, which you may not have heard of and have probably never used, actually does RAID with the Hamming codes on a bit level. But it's so expensive and it's really overkill, so no one ever used it. RAID 4 is a predecessor to RAID 5. The difference between RAID 5 and RAID 4 is that the parity bits are all stored on one drive with RAID 4, whereas with RAID 5 they're across all the drives. So the only benefit of that is that random reads are going to be way better because you know where everything is. But with RAID 5 it's split across, and so that's a lot better for a number of reasons. How does RAID 5 work? We can do this by running an exclusive OR on our data to get the parity bytes. So I've put 3 columns here, and you can see each one is a drive. So for the first 2 drives, if we run an exclusive OR on these 2, we get 11. And then if we do it again for these 2, so I'm distributing the parity across the different drives, and you can see over time how the parity is calculated. And these are parity bytes as opposed to parity blocks. Cool. So now we have, for the set of black data we have some green data which we're adding, and this is going to be our parity. So we lose a drive, bam. We can run exclusive OR again on all the other drives and just very simply recalculate the drive. So it's really straightforward and works quite well. So Hamming codes were in the 50s, and that was quite straightforward. RAID has been fairly straightforward so far. I think we're all following. Then along came these guys, Irving Reed and Gustav Solomon. And these guys were mathematicians and worked at the MIT laboratory. So 10 years after Hamming's paper, they published a paper called Polynomial Codes over Certain Finite Fields. So this is where it gets a bit complicated, right? So I was reading about Reed Solomon, and I suddenly realized that I was way out of my depth. So what do I do when I'm way out of my depth? I always go on IRC, never fail to make the same mistake. And so I went looking for the right IRC channel to ask, and thinking that this would be helpful. So I asked this question in an IRC channel that I knew had about a dozen mathematicians in there. And this is the response I got. So I have no idea what any of that means. I still have no idea what it means. But essentially, I did a bit more reading, and the main idea was that this revolves around something called Galois Fields. And this is basically a finite field. It's a mathematical concept where you can have a set of a size of a prime number, and you can conduct any operation on the values within that set, and the result will also be within the set, and you do this using modulo. And it has lots of special properties, and you can put numbers in there, you can put polynomials in there, you can put roots of polynomials in there. But essentially, the way this works is that you can sequence any set of data, you can express that as points on a graph, as a polynomial. And then if you take 3, 4, 5 points on a certain polynomial, you can then use interpolation to find a few other points on the same graph. And that's the fundamental way that Reed-Solomon codes work. So you define a code, and then you can use that on both sides to recover data. And it's highly efficient, but it's also more computationally expensive. So here's an example of how that works. K is commonly used K and M. K is the number of data shards, and M is the number of code shards. So on the left, you have a distribution or generator matrix, and this is what you multiply by the data. And some of you that are familiar with maths will recognize this as an identity matrix, so this is equal to 1. So you're multiplying the data by 1 at the top, and at the bottom you have a code, and you're multiplying that, and you get your parity bits that way. So, so that's how you do it on the encoding side. And then on the decoding, you just take the inverse of your original code, and you multiply it by whatever you've lost. So in this case, if we lost D2 and D4, we can substitute the parity bits there, multiply it by the identity, the inverse of our generator matrix, and that will give us the original data that we had. So as you can see, this is a lot more efficient than Hamming codes or parity bits. So this is what Erasure coding looks like in Ceph. So this is for k equals 3 and m equals 2, so 2 parity shards for every 3 data shards. So in Ceph, when you create a new pool, you can choose whether you want it to be triple replicated or Erasure coded. And it has a pluggable architecture, so you can specify which Erasure code you want to use on a pool-by-pool basis. Obviously, once you've chosen a code, you can't go back. So be very certain that you've got the right code before you put loads and loads of data in there, otherwise you're going to have to migrate, and it's going to be painful. Almost all of the Erasure coding plugins within Ceph rely on some form of Reed-Solomon. It's the way they pretty much do everything. There's a number of different varieties of Reed-Solomon, and they have different strengths and weaknesses. Some are more efficient, some are less efficient, but pretty much all of them use Reed-Solomon. It's worth mentioning also that lots of other things use Reed-Solomon. So CDs and DVDs, they also use Reed-Solomon. So if you ever wonder why you've got a very scratched CD and it still seems to work perfectly, that's because Reed-Solomon is behind that. It's also used by pretty much every barcode ever. So if there's a damage to the paper or damage to the barcode, you can still read it in most cases, and that's thanks to Reed-Solomon. So yeah, I mean, it's also used heavily in data storage. So most implementations of RAID 6 will also use Reed-Solomon. So in terms of new Erasure coding plugins within Ceph, or what's in the last 10 years or so, there's a few different ideas. One is called the shingled Erasure code, or SHEC. And the goal of that is to be more configurable than Reed-Solomon and better at recovering data, but it's still very new. There's also an implementation called Clay, which focuses on reducing network bandwidth. And there's another concept called locally repairable codes. And with locally repairable codes, you can have another variable that you specify called L, and you can specify how many additional parity bits you'd like, and then you can distribute them. And the idea is that you can distribute more parity bits within the cluster. So if you have a very large cluster that's geographically replicated, you have more chance of a parity bit being close to the data you want to recover, and so it's not going to be very expensive in terms of network bandwidth. So the key thing to remember is that you need to choose the right numbers for K and M, and think about how durable you want your cluster to be versus how much it's going to cost you in redundant storage. So yeah, this is very much a trial and error game. So what's Soft Iron doing in this space? So I don't know if you've seen, there's been lots of announcements around it recently, but Soft Iron has a set of different storage servers. They're specifically designed for Ceph. They're I/O machines, they're ARM-based, and they're great at getting data in and out, but not necessarily great at doing compute or solving compute problems. So this is an ideal scenario for a storage server where we don't really want to be doing much compute, and we want a lower cost per gigabyte and a longer lifespan for our hard drives. So it's great for operating a large-scale cluster, but there's some operations we want to do within Ceph that are expensive. So compression, encryption, Erasure coding, these are all examples. So what Soft Iron is working on is a NIC design with an FPGA on it. And the idea is that we can take a few of these concepts within Ceph and do them in hardware. So an offload. And that's it, that's my talk. If you have any questions?
Sorry, this is really silly. Have you, in your research that you've done for this, encountered the fact that whereas Ceph in its documentation always talks about K and M, most of the literature talks about something like, I think, K and N, where N
yes,
is,
yeah.
right?
Yeah.
Have you any idea where that comes from, or why Ceph uses terminology that's kind of not in line with the scientific literature?
There's also T as well.
Right.
Yeah. So I think I think N was the size of the data shards plus. So it's the size of the overall data shards and the parity shards. And K and M is. I don't know why Ceph has chosen to do that. I guess. I mean, in a certain regard, you probably only really need N or M. You don't really need both.
Yes, of course.
Yeah.
K plus M equals N.
Yeah. So if you have two of them, that's enough to feed an argument to the plugin, right, and tell it how many I want. And then there's T, which was the size of the Galois field. And so you have G of T, and T is always going to be a prime number or power of a prime number, because that's just a property of what Galois field does. But Reed-Solomon will do that all for you. So it breaks up your data into a number of fields that are all the size of prime numbers, and it uses that to do it.
Is the offload work that's being done there at SoftIron, is that a lot of the Erasure coding, or what's the biggest kind of computationally intensive part that's being offloaded to the NIC?
So currently, yes, it's the Erasure coding. I think we can do anything with the FPGA. So we can define any sort of hardware design we want. But at the moment, the idea is, because Ceph has this pluggable architecture, you can take out any Erasure coding plugin and replace it with shim and have it all done in hardware instead. But it's about figuring out the trade-off. In some cases, it may be, depending on what the operation is, it may be more sensible to do it at the CPU. And in some cases, it's more sensible to do it at the FPGA, because there's an expense to sending it to the FPGA and bringing it back as well. But it depends on the workload.
Danny, I was going to ask about that architecture as well. So is it, for that particular use case, is it more efficient to use an FPGA there, rather than, there's off-the-shelf stuff now from folks like Mellanox with ARM cores directly on the NIC? Is it
Sure.
Is it still more efficient to do for that particular workload to offload to FPGA?
So it's the same sort of thing, right? Each one of them is an offload to hardware. I think the good thing that FPGA gives us is the ability to do a whole number of things, whereas with an ASIC, it's been designed for one thing and one thing alone. So we would have you're going to need different hardware if you want to do something else clever with compression or with encryption. Whereas with an FPGA, we can constantly write.
What I was getting at is that there's newer generation of cards coming out which have actually got general purpose ARM cores available directly on the NIC, as opposed to going out to that you've got a general purpose processor there rather than an ASIC.
Yeah. I mean, so you don't have to what? So what's the difference between?
Well, I was just saying, is it more efficient, because there's obviously FPGA works very well for certain kinds of workloads, and whether that is more efficient using an FPGA than using a general purpose processor, right? That network layer.
Sure. I don't know the answer to that question. No, it's all right. I'd have to play with some of the other stuff that's out there, but. I think the reason why it's an FPGA from a SoftIron perspective is because it's really flexible. But I can see why some people are doing ASICs as well.
So are you doing this testing with the kind of the NIC offload, with the Erasure coding in there? Outside, my understanding is SoftIron is doing it all with the ARM processors, but it seems like that would be really helpful on an Intel platform as well, because then you can just use a much lower cost chip, because most of the work is going to be offloaded to the FPGA.
Yeah, so we have an Intel design coming as well. Yeah. The ARM chip is really good because it's just so low power and it runs really, really coolly. And one of the things that SoftIron is aiming to do is density, get as many nodes into a rack as possible. And so you don't really want 42U running really hot, but there are things that you want to do that are more computationally expensive within Ceph. And so the idea is to have a whole set of different designs, and then you can sort of pick and choose from different ones to put together different Ceph clusters as on a case-by-case basis.
Outside of the Erasure coding, is there something else that you guys are working on putting into the the FPGA or other components?
Yes. Yeah, I know at the moment erasure coding is the main focus, but I know there's plans for compression and encryption as well.
And what about like Intel's got like their QAT and some, they've got sort of that compression offload and some other encryption. There's the ESNI, but now there's some newer stuff that's in the Intel chips. Are you working on plugins to tie Ceph into that, or is there already plugins for that?
I actually know the answer to that. Sorry. That's an interesting question. I'll have a look at that afterwards if you want.
Sure.
Cool. Thank you very much.